All right, y'all, let's get started. So we're still going through this unit on categorical variables, still going through the same readings, Judge Chapter 8, now Chapter 9. You ought to be on Chapter 9 if you want to keep up with the readings. And on Wednesday, we're going to be covering some content that's a little bit unrelated to the Judge chapters. So we'll be going off on a slight detour. But it's connecting back with some themes that we've talked about last semester, actually. And then we're on to something new for Monday. Still on categorical units, but on to new content. There will be a different reading with that. I've been following along this schematic representation of different cases you might cover with categorical variables. So we finished our custom contrast unit. We're done with that. I might have one other example on Wednesday that deals with contrasts, custom contrasts. But you have the tools that you need to handle that specific case. So we're moving on to the second case, which is still, you still have some planned comparisons that you're interested in. But they're no longer going to be represented by custom contrasts. And I'll show you a couple of the differences as we go through the unit. And there's a bit of terminology that I want you to know. Dummy coding, dummy codes. This is another thing that you'll see pretty often in papers. I won't tell you what this is just yet. I just want you to know that this type of contrast that's still planned is going to fall under the name dummy coding. So I'm still going to continue on with the same research scenario, looking at drinking and anxiety. And actually, we've got a similar design as when we were looking at the custom contrasts. So we're getting 1/3 of the people drunk on vodka and Tang, 1/3 of the people are not drinking anything, and 1/3 of the people are drinking a placebo. We're still looking at startle response as a measure of anxiety. But our hypothesis is different. So this is the planned part. We have a specific hypothesis that we're interested in, but it looks a little bit different from when we were looking at custom contrasts. So specifically, we're predicting that both alcohol and expectations about alcohol as manipulated by the placebo. Both have an impact on anxiety, but we're not sure how the effects of alcohol are going to compare with the effects of expectations. We just think that both of them are going to have some sort of effect. So this looks a little bit different from the hypotheses that we were looking at before, because last week we were always making some specific predictions about how alcohol and expectations about alcohol would compare to each other. So we had fully laid out we fully mapped out exactly how we expected the means to turn out when we did so. And in fact, we tried to capture that the stuff that isn't inconsistent with our predicted pattern using those residual contrasts. Well, now we're being a little bit non-specific about how alcohol and expectations about alcohol compare to each other. So that's the major difference. And this difference actually has a lot of implications for how we treat the design, or how perhaps I would argue that we ought to treat the design.
Gotcha. So is that looking at expectations of direction, directionality in the relationship, and then also magnitude or degree to which they have an effect? Looking at both?
So here we're just being non-specific about it. So we're expecting that compared to nothing, alcohol will do something, and compared to nothing, expectations will do something. We're just non-specific about how alcohol is going to compare to expectations. So we have directional hypotheses, and I guess we're not predicting a specific magnitude here. The major difference from what we were looking at before is that we're not specific about how alcohol compares to expectations. There's something that is unpredicted. That's not fully mapped out. Is that answer your question? So let's just imagine that this is what our data set looks like. And we still haven't replaced these text labels with numbers that the general linear model can handle. So of course, that's going to be our major task, is figuring out how to replace these text labels with numbers that, in a way, that captures our predictions. So that's what our end goal is. And I'm still going to make two mechanical variables that capture our predictions. They're just going to look a little bit different from what they did before. And if you think back to the approach that we took way back when we first learned about categorical variables, the first thing that we did is we just replaced two of the groups with arbitrary numbers. And it seems like for one part of our predictions that, say, alcohol will have an effect as compared to nothing, we ought to just be able to replace alcohol with a number and nothing with a number, just as long as they're different. And that'll capture that comparison. So that at least gives us a starting place for how to replace these text labels with numbers. So that's what I'm going to do. Right now, I'm going to work with the numbers 0 and 1. And I'll talk a bit about why I'm doing that as opposed to other numbers in just a moment. But for now, what I'm doing is just I'm trying to apply the same kind of technique that I did way back when we first learned about categorical variables. So okay, that's part of our predictions where we're trying to compare alcohol with nothing. With the other part, we still need to compare placebo with nothing. So maybe we can just replace placebo and nothing with those arbitrary numbers, just like we did with alcohol and nothing. So there are my two numbers. That ought to get me a comparison between placebo and nothing. But I'm still not quite finished because I haven't filled in this entire table. I still need to put numbers under contrast 2 for alcohol and under contrast 1 for placebo. And I don't know if you're going to be able to guess what numbers go there. Actually, what I'm going to do this time is I'll just show you the numbers, and then we'll go through why they might make sense. I think this one's a little bit easier to grasp the intuition of after you've seen the answer and had a chance to look at how it works. So what I'm putting there are more zeros. So there are a couple differences between this kind of contrast or this kind of coding scheme, rather, the set of contrasts, and the sets of contrasts that we've worked with so far. So first of all, just a bit of terminology. This category that gets zeros the entire time for both contrasts, that's called a reference category or a reference group. So I'll describe why that's true in just a bit, but just note that I'm going to be using that term, reference category or reference group. So, okay, first of all, this is a set of dummy codes. That's another bit of terminology. Terminologies, I don't know why they're called dummy codes, honestly. I don't think they're dumb. I don't think they're dummies. That's just what they're called. And it's very standard terminology. So you'll see that all over in psychology, but also in economics or any sort of social sciences, you'll see this terminology. So it's safe. So to describe how these are different from the planned orthogonal contrast that we've been working with before, well, one difference is that they're not signed. So if I take the average of 0, 1, 0. That average is 1/3. It's not 0. Likewise, if I take the average of 0, 0, 1, it's also, the average is also 1/3. So, okay, they're not centered. That's important. There is one similarity between this type of coding scheme and the ones we've looked at before. These are unit weighted. So again, unit weighting means that the distance between the minimum value and the maximum value is long. So that also has some implications for interpretation later on. The one last difference from planned orthogonal contrasts is that these are correlated. They're not orthogonal. That might be a little bit hard to see here. But if I ask R to tell me what's the correlation between 0, 1, 0 and 0, 0, 1, they're fairly strongly correlated. So minus 0.5. And to see why that might be true, we'll just notice that both contrasts are using the same reference category. So in each case, I'm giving the number 0 to contrast 1 and contrast 2. That would have to be different in order for these to be uncorrelated. So that's one of the reasons why it's like looking at the numbers themselves, is that they share a reference group. But it turns out this feature of having some sort of correlation, some degree of redundancy, some non-independence between the contrasts, that's very important. And that creates some special interpretations that are actually pretty useful for addressing the hypothesis that we started with. Questions? Okay, so I have some graphs to show you how this works. But first I want to show you what it is that we've done, what information we've actually captured with these contrasts. So here, all I'm doing is I'm creating two mechanical variables, C1 and C2. I'm just using the same processes that we used for planned orthogonal contrasts. So I'm using case underscore when. You can also use the use factors in R and use those to create your contrasts. Oh, I was supposed to make an announcement while I'm thinking about that. I was supposed to make an announcement for Austin that in order to make your graphs, you can just rely on the factors. You don't have to create contrast variables and then use those to graph. You can just, create a factor and use that to get your predictions, and like you can just follow through that process without bothering to create contrast like I'm doing here. Because I understand that a couple of people have questions about that. But anyway, so here I am creating the contrast variables. Part of why I like to do that when we're doing model fitting is that it helps me grasp exactly how I'm treating this categorical variable. It makes it very explicit how this is all working.
Would you mind walking through that script?
Sure. So I'm using mutate to create new columns, new variables in my data set. That second line says, one of my variables is going to be called C1. That's going to be the name. Case when allows me to give create one number if one condition is satisfied and other numbers if another condition is satisfied. So this says when my factor variable with the text labels is called treat. So when treat has the label alcohol, I want this to be a 1. Otherwise, I want it to be a 0. So if we look over here at contrast 1, all I said is in that middle column, that's when I want to give it a 1. Otherwise, I want to give it values of 0. So that's just going to create a variable that's 1 if treatment is equal to alcohol, 0 is otherwise. The second variable that I'm creating is I'm going to call C2. And this next bit says when treatment is equal to placebo, so if that's the label, I want to give it a 1. So that's the second row or column. Otherwise, I want to give it a 0. You might have worked with if-else. Case when is in tidyverse. It does what if-else does, but it's a little bit less cumbersome in some circumstances. They basically accomplish the same thing. So there's no problem at all with using if-else if you find that important to you. One thing that's nice about case when is that you don't have to nest case when. So sometimes with if-else, you have to do nested versions of if-else, like if this is satisfied, do this, otherwise, if this is satisfied, do this, otherwise, if this is satisfied, do this. It gets kind of hard to read. Yeah, this doesn't have that problem. Everybody understand what's going on? Okay, so next I just fit the model like we had before, and here are the parameter estimates and standard errors, T, E, etc. So in order to see what this is actually doing, I'm going to give you a table of descriptive statistics. So I think I've used this in class before, described by, I find it very handy for getting lots of descriptives very quickly. So here are the means and standard deviations within the group. So let's start with that intercept. I won't make you do this, but if I forced you to search through this table to see where that 65.53 shows up, here it is. So this is, again, different from when we worked with planned orthogonal contrasts, because the planned orthogonal contrasts were always centered, which meant that that intercept was always the great mean, the mean of means. Here, actually, that intercept is one of the 3 means that we're working with. And specifically, it's that reference category. So it's the mean of the nothing group, the group that neither had a placebo nor had any alcohol. So we want to select the reference category is going to be the intercept. We look at C2, or C1 rather. C1 doesn't appear to be any of these 3 means. So it's not just a mean, it's probably a comparison between means. And specifically, it's a comparison between our reference category, which we just saw before, and our alcohol category. And more specifically, it's the alcohol category minus the reference category. So you can think of this as the degree to which predicted anxiety changes as you go from the reference category to the category that has more alcohol. Anybody want to take a guess as to what C2 is going to be?
The difference in means between nothing and placebo?
Absolutely. So if we follow the same pattern, just matching patterns, seems like this probably ought to be what happens when we go from nothing to placebo. So the reference category is the category that has a 1. And exactly what it is. So it seems like we've set up a set of contrast values that capture comparisons between the category that we care about, our reference category, and the other categories. So this is a series of mean differences, specifically mean differences as compared to some reference category. And we think back to the hypothesis. Our hypothesis was framed in that way. So the hypothesis said something about how alcohol and expectations will compare to nothing. They just didn't say anything about how alcohol and expectations will compare to each other. So it seems like we got what we were looking for. This is a little bit weird though, because if you think about each of these contrasts on their own, so for C1, for example, nothing and placebo are both coded 0. So it seems like, I mean, if you were just looking at that on its own, it seems like maybe that contrast ought to be comparing both nothing and placebo, the average of those two, to alcohol. And that's the way these contrasts worked when we were looking at planned orthogonal contrasts. So you could look at the contrast on its own. Anything that was like matched together was basically averaged together. But that's not what's happening here. And the reason for that has to do with those special features, those differences between dummy codes and planned orthogonal contrasts. So one was a special category, our reference category, always gets a 0. And the second thing was that these dummy codes are not orthogonal to each other. They're non-independent. And just like when we were working with non-independent variables in other contexts, so if we had two quantitative variables that were correlated with each other, that means that there has to be some sort of adjustment process. As we interpret one, we have to sort of hold constant the other. We sort of adjust for the other. And that's something that has to happen here too. So when we're thinking about the interpretation of each of these coefficients for C1 and C2, you have to think about holding constant C1 or C2. That's a little bit difficult to think about. So I've got a couple graphs here that I hope will help you build that intuition as to why this might be true. So the first thing that I'm going to do, sort of like we've done for other categorical designs, so I'm just going to color code each of these sets of points. Now I'm going to plot on the x-axis each of these C1 and C2. So I'm just replacing these text labels with the numbers that we came up with. So, okay, this is C1 on its own. This is what happens when you plot C1 and ignore C2. And what I'm going to do is basically subtract out the effect of C2. So I'm basically taking C2, its predicted effects on anxiety, and subtracting that out of the graph. And I'll show you what happens to this set of points, everything, as we go from C1 to C2. So I'm literally doing some subtraction. That's it. I'm taking the effect of C2 on startle, on anxiety, and just subtracting it out. So an interesting thing that happens here is that only the placebo points are affected. So notice how placebo in C2 is the only variable that gets a 1. So those are the only points that end up getting adjusted. Everything else stays the same. It's like I'm subtracting out the mean difference between placebo and nothing group. So you can think of the process of adjustment as like subtracting out the effects of other variables. Well, just in that way, sort of what I'm doing with these dummy codes is I'm subtracting out the other comparisons that aren't plotted on this x-axis. That's sort of what you're doing when you adjust for the other dummy codes. Once you do that, you can find that best fitting line on the adjusted data. Just like we have for any other extension to the general linear model, you pivot that line and you find the one that minimizes the sum of squared errors. And if you do that, the slope of that line on these adjusted points ends up being the mean difference between alcohol and nothing. And that's because we've subtracted out anything that placebo is doing.
So now your placebo points beforehand are basically the same as a nothing group?
Yeah, the mean is exactly the same as the nothing group. There's still some spread. There's some variability in the placebo group. Like some of the points in the placebo group are too low, some of them are too high, and that contributes to the calculation of the sum of squared errors. And you still have, instead of like having, so there are 100 participants in each group, I have 300 points total because I still have the placebo group in here. I just adjusted up the mean of the placebo group to match the mean of the nothing group. It's a really good observation. Yeah, you got it right. So I could do the same process with C2. So now placebo is the thing that gets a 1, nothing and alcohol both get 0s. And if I subtract out the effect of C1, the thing that you have to control for in order to interpret C2. Notice now the only points that get affected are the alcohol group. They all move up by the same amount. So essentially, to build on the intuition that you have, I'm adjusting the mean of alcohol so that it matches the mean in the nothing group. I then find that best fitting line that minimizes the sum of the squared errors, the sum of the squared prediction errors. The slope of that line ends up being the mean of the placebo group minus the mean of the nothing group. It can be a little hard to get a good intuition on why this works because it relies on that idea of adjustment. Adjustment is one of the more complicated subjects in the general linear model. One way you can think about that is when you adjust for something, you subtract out its effects before you look at benefits. Yeah.
So I think I'm following all this just fine. I'm just curious. So if the effects for C1 and C2, calculating those effects are contingent on knowing the effects of the opposite. Mm-hmm. So I mean, it's just under the hood some sort of iterative process.
Yeah, I mean, technically you can use matrix algebra. That's a branch of math that I haven't talked about very much. But if you really want to know the mathematical details on the matrix algebra textbook, that's a really good way of understanding this. Another way of getting at is that sort of iterative process. And a lot of statistical techniques rely on that kind of iteration. We'll see another example when we get to within subjects of science where that iterative process is actually how the algorithm works. So it's a perfectly fine way, and I think an intuitive way of figuring out, of understanding what's happening under the hood. Okay, so this is the set of contrasts that we ended up with. And we found that each of these contrasts represents a specific mean difference. Specifically, the difference in means between the reference group that's always staying the same and the group that has a 1. And the reason that's true relies on the fact that as a set, the contrasts are correlated with each other. They're not independent. And so under the hood, when you interpret these coefficients, you have to like adjust for, subtract out the effects of the other contrasts. And that's really important. So if you're using dummy codes, you have to include all the contrasts that you create. Otherwise, those coefficients won't have the correct interpretation. So we learned with planned orthogonal contrasts, the biggest reason to include those extra contrasts, the residual contrasts, was because of this issue of residual between covariance, the stuff that's going on that's not captured by the contrast of interest. Here, actually, the interpretation won't even be correct unless you include all the contrasts. So that's another difference from planned orthogonal contrasts. So the fact that these contrast variables, these mechanical variables, are correlated with each other also means that if you look at the variance-based effect sizes, so here I just asked for the change in R squared due to each variable. That's a common variance-based effect size that we talked about last semester. So I'm looking here and here. So if you look at the variables as a set and look at how the set of variables contributes to R squared, it's the same regardless of whether you're looking at dummy codes or if this is a set with planned orthogonal contrasts. Not important. I'm looking at the linear quadratic contrast. This will always be true, regardless of which particular orthogonal contrast we're working with. But another difference from planned orthogonal contrasts is that if you look at the change in R squared due to each individual variable, that sum does not equal what happens if you look at the variables as a set. And that is, again, because these variables are non-independent. You have to think about each other variable as you're interpreting or thinking about how it helps you explain the variance in the outcome. Whereas with the planned orthogonal contrast, the fact that those variables were uncorrelated with each other means that if you take this sum, it will exactly equal the sum of those variables considered as a set. So this sum is a bit too high. This sum exactly equals this number right here. I'm more talking about this to link up to concepts that we considered last semester. I find when I'm writing papers, this particular feature of delta R squared is not something that I have to think about most of the time. I usually just think about mean differences. But this is similar, or it links up to some of the principles that we talked about when we were talking about controlling for things. That the fact that these two variables are overlapping means that they kind of do weird things when you're thinking about R-squared. So this is essentially how dummy codes works. You follow a procedure where first you think about what your reference category might be. This might be during the planning stage, for example. And when you're actually doing the analysis, all you have to do is create variables where you're trading off what gets the one. So for the first variable, one thing will get the one, and then you switch it for the second variable if you're considering a 3%. But I've hidden some complications from you as I've been introducing these ideas. The first of those is that there are some comparisons that go into these that I could make of these group means that seem to be missing from what I showed you. So specifically, if I go back to this table of means, I was always comparing the reference category to either placebo or alcohol, but this comparison between alcohol and placebo isn't there. It's just gone, which seems kind of weird. So if I'm trying to look at this model output up here, now I'm trying to find, hey, what's the comparison between alcohol and placebo? I can't find it. The reason for this has to do with the mathematical properties of like addition and subtraction. So specifically, you first consider C1. C1 ended up being a comparison between nothing and alcohol. C2 ended up being a comparison between placebo and alcohol. Once I've determined those two differences, I can use them to figure out the last difference. So I take C1 minus C2, that's this quantity minus this quantity. And if I just do the algebra, this nothing group cancels out. That is to say, just due to the properties of addition, if I find out what these two comparisons are, I've already determined that there's only one answer for what this last comparison could be. It's fixed, it has to be true. This is one way of understanding. Back last week, I talked about how in order to fully represent, say, 3 groups, I needed 3 minus 1 mechanical variables. This is that principle in action right here. So I've got 3 groups. In order to represent 3 groups, I only need 2 mechanical variables, because once I fix those, once I figured out the values of those mechanical variables, the third comparison that I might be interested in can only take on one quantity. It can't take on any other quantities.
And that's going to be a negative 26, right? Alcohol is going to result in a decrease of 26.
Oh, yes. Yeah. I'll fix that. So that should be a negative. Thank you. So if that gets me the specific value of this mean comparison, but if I want the statistical test, I I have to change the reference category. So specifically, I might set up a set of dummy codes like this, where now placebo is the reference category. It's the thing that's always getting a 0. And then I fit a new model with those modified mechanical variables with the difference reference category. And you'll see that C1 up there ends up being that missing comparison. This is actually a really important principle when thinking about dummy codes. Because often one might have the temptation to look at like all possible comparisons. So this is a way of getting what's called pairwise comparisons. Pairwise just means I'm taking two groups and comparing their values, comparing their means. So this is a way of getting pairwise comparisons. And if you have three groups, there's a strong temptation to look at all three possible pairwise comparisons that you get out of these three groups. But if you do that, you have to fit in a new model. You have to fit an extra model. You're kind of exceeding the number of comparisons that are possible to look at statistically using one model. And you can imagine that this problem might get even more complicated if you have 4 groups or 5 groups or 6, because there are a lot more pairwise comparisons that are possible when you add the increase in the number of groups. I'm not going to talk about the resolution to that problem just yet. That's going to be the topic of next month. But I want to plant that seed in your mind that when you're looking at pairwise comparisons, often lots of pairwise comparisons are possible. Maybe so many that it feels like you run the risk of getting something wrong. You run the risk of accidentally saying that there's a difference when there's not. For now, just know that if you're doing this sort of planned set of comparisons, it works best if you focus on 2 of them. And in order to look at 2 of them, it's often very convenient to set a specific reference category and compare like each other group to that reference category. I'd say the best case scenario, the research scenario that fits best is if you have one group that's kind of important to it and the others can be thought of in comparison to that important group, so like a control group, for example. Any questions on that?
We're doing this because we didn't have those previous expectations of what was going to happen.
Yeah, and that has some implications that I'll talk about very soon. I guess just to get a sense of what the general set of problems is. With planned orthogonal contrasts, all of my thoughts about the pattern of means was captured by one mechanical variable. But here, my thoughts about this pattern of means are captured by 2 mechanical variables. So that's kind of different, right? Yeah, that has some implications that I'll talk about very soon. So I guess my answer to this first question, what about the missing comparisons, is that those missing comparisons are implied by the mechanical variables that we've already set up. And that will generally be true. You only need the number of mechanical variables, or the number of levels of the group that you're thinking about -1 mechanical variables in order to represent everything that could be happening. So I've already forecast a little bit how you extend to more complicated designs. We've so far been looking at this 3-group design where we only have 2 mechanical variables. So that's this set of contrasts right here. In order to extend to more complicated designs where you have, say, 4 groups or 5 groups, all you have to do is add an extra mechanical variable and rotate which group gets the one. It's really quite easy. If you want to extend to 5 groups, well, you add one extra mechanical variable and rotate which group gets the one. And notice in general, when you consider each contrast, this contrast, for example, represents the reference group of 1 versus 2. This represents 1 versus 3, 1 versus 4, and 1 versus 5. And you can extend that as much as you like, ad infinitum. So one nice thing about dummy codes is that they're pretty easy to set up. You don't have to go through a sort of rigmarole of figuring out what the residual contrasts are. You just do this. It doesn't require a whole lot of fiddling. So in order to handle more complicated designs, same principles apply as when we were working with plane orthogonal contrasts. You need G minus 1 mechanical variables, where G is the number of groups. So you need 4 mechanical variables for 5 groups. And the only thing that you do is you rotate what gets the one. So I'm almost certain that you've seen alternative ways of handling this kind of design. Again, these multiple category, these variables with multiple categories, 3+ categories, have lots of approaches and not much consensus for how to handle them. So I'm going to go through 2 important ones, one of which is going to finally answer the question that you posed a couple weeks ago, which is, what if you just took 2 of the groups, you deleted the data from the third, and you just compared those 2 groups to each other using a t-test? So I'm going to call this set of t-tests on subset of data. By this, I mean, maybe for one of the comparisons, I just look at group 1 and group 2 and delete the data from the third group, do a t-test. And then the second one, I say, maybe look at group 1 versus group 3, delete the data from 2 and do a t-test. So this is the model that we ended up with, the model that I'll end up recommending. This is what it looks like if I subset the data. Well, I guess one of the parentheses is missing at the end, but all this is doing is it's fitting the model with C1. The data set that I'm using filters out all the data from the placebo group. So what this is going to do is it's just going to give alcohol a 1, nothing a 0. And I'm not even considering the data from the placebo group. So the first thing that you can notice about these 2 models is that they both give you the same mean difference. So they both give you the same coefficient for C1. That ought to make sense. We've worked with independent sample t-tests, so cases where we just have two groups, and we could have numbers of each. And we saw that in those cases, you get the mean difference. We also just saw that you get the mean difference with dummy codes. So you'd expect that those coefficients ought to be the same, or be something deeply wrong if they weren't. What is different is this other stuff. So we look at the standard error. Let me ask a question. In general, do we prefer for our standard error to be larger or smaller? Smaller, and why so? What does the standard error represent? The variance in the sampling distribution. Or another term that I've used is precision. A smaller standard error allows you to observe smaller differences. Notice how the standard error for the model that we ended up with, that includes multiple dummy codes, is smaller than the standard error where we've subsetted the data. So there are two reasons why this is true. One is that with this model up above, we're working with 300 cases, 300 observations, 300 people, which means that our error degrees of freedom are 297. In this model down here, we've deleted 100 observations from our data set. So this is one of the main factors that determines how large our standard error is. In general, if you have more observations, you'll have a smaller standard error. So that's one effect. The other effect is not going to have as big of an impact, but it still matters a little bit, is that our standard error generally gets smaller if we have other stuff in our model that's explaining variance in our output. That's that feature of covariance that can, increase your power and have a helpful impact on your standard errors. Well, in this model up here, we've got C2. That's that other thing that could potentially explain variance in output. So to the extent that C2 captures real differences between means, that'll make the other, the standard errors in our model small. So notice how the same principles that apply to any sort of multiple regression model also apply here. These two things that can have a big impact on our standard errors still have that same impact. So this should answer your question about why, in general, when you can, you want to prefer not doing this subsetting. There's one special case where you might have to think a bit more carefully, and that's if one of your groups has a standard deviation that's way different from the others. Because we go way back and look at this graph, notice how we're kind of assuming that the scatter of the green points is the same as the scatter of the gray points. If the scatter of the green points was way different, that would be violating the constant variance assumption. So I'm not going to go in huge detail about what to do in that specific case, because in general, violations of constant variance are not the hugest deal in the world. There's a big literature on what to do in that specific case if you're interested and want to know how to do it. Actually, though, the same tools apply as what we looked at when we went through our unit on model assumptions. But the big take-home point that I want you to get is that you ought to prefer this dummy coding approach to looking at subsets of your data when you can, because it gets you more observations. You don't throw out information.
And those differences would be more pronounced too with smaller sample size.
Yes, absolutely.
You'd like 10 for the group.
Yeah, I mean, you wouldn't want to be working with a 10 per group design in the first place, but sure, if you were to do that, you'd be, well, in any case, you'd be throwing out a third of your data, but if you're working with 10 per group, the marginal effects of extra cases are much more pronounced when you have a small sample size than if you have a really general sample size only. Absolutely. Okay, so that's one alternative that I think just in general is less preferable than the dummy coding approach. I'm just showing you, you get the same impact on standard errors if you look at C2 compared to if you subset out the there's actually one other reason why you might not want to subset out your data that we'll dig into a little bit more on Wednesday, and that's that if you want to make your model just slightly more complicated. So for example, test for interactions between, say, the dummy code and some other variable. It's not obvious how to do that if you've subsetted your data. It's completely obvious how to do that if you follow this approach using dummy codes. So if you want to make modifications to your model, make it slightly more complicated, this provides an easy way to do that. It's really unclear if you're looking at subsets. So the second approach that I'll consider is the one that I said was generally bad for planned orthogonal contrasts. And that's this approach of testing a joint hypothesis, often called an omnibus ANOVA. That's the hypothesis where you're saying, let's test if both C1 and C2 are 0, and see if either of those conditions are violated. So this is where the model that we ended up with, and this is what it looks like if you test that joint hypothesis. So you fit a compact model where both C1 and C2 are 0 because they're not estimated. And then you compare the model that we ended up with to that compact model. Something that we learned with when we looked at planned orthogonal contrasts is that this F value right here was literally the average of the F value for C1 and the F value for C2. Except that in planned orthogonal contrasts, we're only interested in one of those F's because we only think that C1, for example, our focal contrast, is going to be non-zero. In fact, we're hoping that the other contrasts are close to 0 because they're capturing other stuff that's happening in our groups that are not captured by our C1. So that was really a problem. The fact that if you test this joint hypothesis, this F value is the average of the F value for C1 and the F value for C2. But here it's not so clear. So first of all, it actually isn't true in this specific case. And in general, with dummy codes, it won't be true that the average of those two will equal this. That has to do with the fact that, again, these dummy codes are overlapping. They're not orthogonal to each other, they're correlated with each other. That's why that's true. But the other issue is that we sort of are interested substantively in both C1 and C2. So it's like our hypothesis is spread out across two different contrasts. The reason we had to do that was that we basically couldn't represent our hypothesis in one contrast. So we were saying, hey, we're not sure how placebo is going to compare to alcohol. We're not willing to make a commitment about what that comparison is going to look like. That's actually the thing that forced us to represent our hypothesis using two contrasts rather than one. But the price that we pay by doing that is that when we're looking at our interpretations, well, we spread our hypotheses out across two contrasts. And it's just not clear, like, one of those is true, does that falsify our theory if both are, or like, how do we think about the impact of this joint hypothesis on our theory? That also means that this might be a case where we actually want to control our probability of making at least one error. So we might be interested in this adjusted F value because that adjustment might prevent us from saying that there's a mean difference where there isn't one. I'm going to talk a lot more about that idea when we get to next Monday's class. We're going to talk about adjustments for multiple comparisons. The principle that I want you to think about right now is that because we spread our hypothesis out across two contrasts, we haven't loaded it all on one. It can complicate when we say the data support our theory and when they don't. It just makes that process a little bit harder. So I'll talk more about this idea of doing an omnibus test on Monday. For now, I just want you to know that this is an approach that we've considered before, and it might be a little bit more appropriate in this specific case, but it's not new. I guess, oh yeah, go ahead.
I was just going to ask if these in your mean formula there, what numbers that was referring to.
I changed the data set. This should be 46.31 and 14.69. I changed the data set a little bit. I guess I didn't roll out those changes there, so I'll fix that. Sorry about that. These numbers are correct. I just forgot to change these. So the situation where we really might need to think about these omnibus tests or some sort of method for making sure that we're not making statements that are wrong is if we're dealing with a lot of groups. So 5, 6, 7, 8, because each group we add forces us to add another mechanical variable. If you've got 6 mechanical variables and you're doing 6 tests, you might make a mistake just because that's the way the null hypothesis significance testing works. 5% of the time that the null hypothesis is true, you're going to get a significant result. So I think in a 3-group case where you're using dummy codes, if you can really make the case that both of these variables capture an important part of your hypothesis, and if it really is not important to you how, say, placebo compares to alcohol, you might be able to get away with no adjustments, so not doing this omnibus approach and just going straight to C1 and C2. You might be able to make that case. It's going to be pretty hard to make that case if you have, say, a 5-group design where you have 4 of these variables nearly in the middle. I think your you're on much cleaner territory if you're working with planned orthogonal contrasts. If you have a hypothesis that you thought about in advance, and you can make firm commitments about how all the groups compare to each other, that's much cleaner. So we'll get back to this issue. We'll reconsider omnibus novas or joint hypotheses when we talk about this on Monday. The upshot is, the takeaway is that if you have a small number of groups, say 3, and you can make a strong case that one of those groups is the main comparison group, and you don't care about those extra comparisons that are implied by your dummy codes. And preferably you pre-register all of them. You might not need to do the omnibus node. Questions? So, overall, dummy codes are one way of getting these pairwise comparisons between variables. And generally what you do when you use dummy codes is you designate one of those groups your reference group. That's the thing to which everything else is compared. That allows you to look at a set of comparisons between that reference group and all of the other groups. In the kind of situation that I think is best suited to planned dummy codes, dummy coded comparisons, is where you have some idea of the comparisons that match your hypotheses, like you don't have the theory, or if you're not willing to make a commitment about how those odd categories that aren't the reference category compare to each other. But again, just to emphasize this, if you can make that commitment, or you are willing to make that commitment, that actually makes your job at the back end when you're writing the paper a lot easier. So I just want to emphasize, you really get benefits if you're willing to make that sort of risky prediction that, say, placebo is going to be higher than control for small and control for large. So that's actually quite nice, and I urge you to try to get into that situation rather than this one. If you are in a position where you're using dummy codes, generally you make G-1 mechanical variables, just like you did with planned orthogonal contrasts. Each one of those mechanical variables represents a specific comparison between the reference group and one of the other groups. Unlike planned orthogonal contrasts, dummy codes are correlated, they're non-independent, and that correlation is what gives them their interpretation of a specific pairwise comparison. So you have to include all the dummy codes if you want your dummy codes to have that interpretation. In general, if you have multiple groups that can be considered one particular categorical variable, and where you're tempted to subset your data to get a specific comparison, I recommend you use dummy coding instead. It'll generally be a more powerful approach. It's also more powerful than looking at, say, an omnibus ANOVA joint test. But of course, there are some complications about which of these variables really represents your hypothesis that might make you go for the omnibus approach. And we'll dig more into that later. So just to give you a sense of where we're headed, this is all the specific content about dummy coding. Because there's a lot of similarities between how the dummy codes work and other ones that we've looked at. There's a lot of that same structure. Where we're headed though is we're going to consider how these different types of coding schemes interface with other types of complications that we've looked at in the general linear model. So interactive designs, for example, or adding a covariance. So that's what we're going to consider on Wednesday, is those extra complications. And in the process, I'll make sure to cover both an example that involves dummy codes and an example that involves planar orthogonal contracts. So you will get more practice, and you also get more practice in that. But this is the only day where we're going to be considering just dummy coding and nothing else. The other place where we're headed, the other place where we'll get more practice thinking about the interpretation of these things is next Monday, where we'll talk about adjustments for multiple comparisons. So I'll give you some extra tools for dealing with that problem of having multiple comparisons that bear on theory. We also have one extra day that I haven't decided what to do with that we could use to cover more content related to categorical variables. So if you do want more review on a specific topic, please let me know. I'm also going to talk to Austin about how things went for trip. So I haven't decided what to do with that, but we could use it for more categorical variable stuff. I also have some other ideas for how to use it, and I'm open to suggestions as well. Yeah.
Is it next week that we're with this weird times, or is it this week next week?
Let's see, I think Austin told me that he's going to a conference next week.
Yeah.
So that means that I'll be covering for all. I haven't heard anything about the timing.
Oh, I thought
It
it
says
was,
this weekend.
Yeah,
You
they-
won't have Friday intros.
there was more information.
I think that's this. I don't want to talk out of turn because I'm not sure. I'll talk to Austin and make sure that it's clear whatever it is that we need to do. Yeah, I'll contact Austin. All right, thanks very much.
What?